Hi, thanks for joining me. Today I've got a fun little number theory style problem for you. We have a set S, and it's defined to be the set of non-negative integers t, for which there exist integers alpha and beta, such that t equals alpha squared plus beta squared. So in other words, it's the subset of the non-negative integers with the property that each number in that set can be expressed as the sum of two square numbers. Okay, we want to prove that if P and Q are elements of S, then their product, PQ, is also an element of S. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so perhaps there are a few different ways of solving this problem, but the way I'm going to show you involves complex numbers, which I think is quite cool, especially in a problem which, is sort of Diophantine-esque. You don't really expect complex numbers to pop out, but the way I'm going to show you uses complex numbers and properties of complex numbers, really basic properties as well, to solve our problem, which is great. Anyway, let's suppose we have P and Q and S. Okay, then by definition of S, that means that there exists A, B, C and D integers, such that P is going to be equal to A squared plus B squared, and then Q is going to be equal to C squared plus D squared. Ooh. Okay, and that follows precisely from the definition of being an element in S. Okay, now let's consider this complex number here, Z, which is going to be A plus BI times C plus DI. Okay, so this complex number times this complex number. Now what we're going to do is consider the magnitude of Z squared in two different ways, and then we'll arrive at the desired result. Okay, so the magnitude of Z squared, let's write it down here, is going to be precisely the magnitude of this thing squared times the magnitude of this thing squared. But the magnitude of this thing squared is A squared plus B squared, but remember that is precisely P, and the magnitude of this thing squared is going to be C squared plus D squared, which is precisely Q. So the magnitude of Z squared is thus P times Q. Okay, so the magnitude of Z squared is P times Q. Okay, so we've worked out the magnitude of Z squared in one way. Now let's do it another way by expanding this thing out here. So Z is going to be equal to A times C, then minus BD, and remember we're subtracting BD because we've got an I times an I, so we get a minus 1 there. Okay, then we've got plus I times our imaginary part, and our imaginary part is BC plus AD. Okay, so we've just expanded out Z. Now, the magnitude of Z squared is going to be precisely the real part of Z squared plus the imaginary part of Z squared. Okay, let's call this thing here T1, and this thing here T2. So Z is equal to T1 plus I T2. Okay, and that's just for, so I don't keep writing out A, C's, B's and D's. Notice that T1 and T2 are both integers because A, B, C and D are integers, and here we're just adding, subtracting, multiplying them, so that we're still going to get integers. Okay, so we get Z is equal to T1 plus IT2, and thus the magnitude of Z squared is going to be T1 squared plus T2 squared. And remember, T1 and T2 are integers, so this thing here is T1 squared plus T2 squared, so the sum of two square numbers. But remember earlier we showed that Z squared was equal to PQ. So in other words, we've shown that PQ can be expressed as the sum of two square numbers, namely T1 and T2, and thus it follows that PQ is an element of S. Okay, I hope you have enjoyed that proof. It's quite a neat one using complex numbers and just some really basic properties about complex numbers, such as the magnitude of the product is the same as the product of the magnitudes. And yeah, the magnitude is the real part squared plus the imaginary part squared. Really sort of day one, complex numbers 101 to solve this problem. And as I say, there are other ways to solve this problem, but I thought this one was really neat. And of course, you can give T1 and T2 explicitly here if you wanted to, but we didn't need to. Anyway, I hope you have enjoyed this this quick video. If you are new here, please do consider subscribing. I make lots of fun maths videos, solution videos to problems, talking about fun bits of maths, that sort of stuff. So if that interests you, please do consider subscribing if you aren't already. Anyway, I'll catch you in the next one. Have a great day.